Welcome to this explainer. Today, we're tackling a high-stakes, honestly incredibly fascinating topic: auditing facial recognition algorithms for hidden biases. Look, we all interact with facial recognition every single day, right? But we rarely get to pop the hood and see how these systems are actually making their decisions, and more importantly, who they might be failing. We're going to break down a complete facial fairness audit project, step by step, to uncover exactly what happens when machine learning meets human demographics.
Okay, let's dive into this, because there is this massive myth out there that artificial intelligence is perfectly objective. We tend to think, because it's just math and code, it can't possibly hold prejudices. But is artificial intelligence actually fair? The reality is that machine learning models are built by humans, and they're trained on data generated by humans. And as we're about to see in this explainer, if we aren't meticulously testing these algorithms, that supposedly objective math can easily mask some deeply ingrained biases.
So here's our visual roadmap for today's safety inspection. We'll start with the AI fairness problem, then move into building the verification model, auditing for hidden bias, mitigating the bias, and finally, we'll wrap up with the final ethical verdict.
Let's jump right into Section 1, the AI fairness problem, and uncovering those hidden biases.
Facial recognition is literally everywhere today: airport security, banking apps, our smartphones. But here's the absolute critical issue. AI models can, and absolutely do, inherit human biases based on the data they learn from. We blindly trust AI to unlock our most private devices, but think about it. If an algorithm is trained primarily on faces of a certain age, gender, or skin tone, it becomes a total expert at recognizing that specific group, while systematically failing others. It's not some deliberate malicious glitch, it's just a direct reflection of the data it was fed. Moving on to Section 2, building the verification model. This is basically the blueprint of an AI.
Now, what's really interesting about this slide is that before we can audit the system, we need to step into the lab and see exactly how a ResNet 18 verification model is built from the ground up. Here's the precise chronological pipeline. Step 1, we load the facial images into the system. Step 2, the system generates what we call triplets, which are just groupings of 3 images. Step 3, we train the embedding model using a mechanism called triplet loss, which I'll explain in a second. And finally, Step 4, we save the trained model artifact so it can be deployed or tested.
Let's look a little closer at that third step. Triplet loss is a really fascinating way to teach an AI. You use an anchor image, a positive image of the same person, and a negative image of a completely different person. Think of it exactly like a bouncer at a VIP club. The bouncer looks at your ID, that's the anchor, then they look at you, the positive, then they compare you to someone else in line, the negative. By constantly practicing this three-way comparison, the AI learns who looks alike and who doesn't, which allows it to authorize entry.
But hey, the bouncer is only as good as their training manual, right? In this project, the model was trained using the UTK face dataset, which is highly comprehensive. It separates gender into male and female, it bins ages from 0 to 19 all the way up to 60+, and it groups skin tones into light, medium, and dark. This breakdown is absolutely vital because it establishes the exact demographic groups we're going to use to test if the model is treating everyone equally.
That brings us to Section 3, auditing for hidden bias. This is where we actually test for fairness.
This is the most critical phase of our explainer. We've built the system, so now we act as the safety inspectors, using 2 key metrics. The first is the false accept rate, or FAR. This is the rate at which the system incorrectly verifies an unauthorized person. To translate that technical jargon into a plain-spoken risk, this is essentially letting the wrong person in. If your banking app has a high FAR, a total stranger could unlock your account just by holding their face to your phone. It's a massive security failure.
The second metric is the false reject rate, or FRR, and this is the exact opposite. It's the rate at which the system incorrectly rejects an authorized person. This is that incredibly frustrating experience of locking the right person out. Imagine standing in the freezing rain, completely unable to unlock your own front door because your smart lock just doesn't recognize you today. Now, the brilliance of this fairness audit is that it doesn't just look at the system's overall performance. It calculates the false accept rate and the false reject rate across the overall population, and then slices that data across those specific demographic subgroups we saw earlier. The logic here is simple but super powerful. We're looking to see if certain age, gender, or skin tone groups suffer from significantly higher failure rates than others. If one group is constantly being locked out, while another group is easily let in, well, we've mathematically proven a hidden bias.
which leads us directly into Section 4, mitigating the bias. Let's see if we can fix the imbalance.
So the crucial point is what happens when we actually find that bias. The developers didn't just throw their hands up in defeat. They implemented a strategy called balanced batch sampling. Essentially, during the training phase, they forced the AI to consume a perfectly balanced diet of data across gender and race groups. By making sure the algorithm spent an equal amount of time learning the facial features of light, medium, and dark skin tones as well as different genders, they theoretically forced the system to become equally proficient at recognizing everyone.
Let's look at the actual results of that fix. The initial model had an accuracy of exactly 0.5000. The mitigated balanced model saw its accuracy rise to 0.5042. So, while the mitigation strategy did successfully produce more differentiated subgroup metrics and slightly improve the fairness-aware performance, you'll notice the overall accuracy remains surprisingly moderate. It's a stark reminder that simply balancing the data batches definitely helps, but it's absolutely not a magic bullet that instantly creates a flawless, highly accurate model.
Finally, Section 5, the final ethical verdict, and the real-world dangers we have to face.
We really have to pause here and look beyond the code. A mathematical imbalance in an algorithm translates directly to unequal real-world impacts. As outlined in the project's ethical considerations, we're looking at lingering demographic performance disparities and the inherent limitations of dataset sizes. Beyond that, there's the ever-present danger of misuse in surveillance systems, where false positive security risks could literally lead to someone being wrongfully identified or detained. These aren't just numbers on a screen, these are sobering risks to daily human life.
And this brilliantly illustrates the ultimate takeaway from this repository. The creator explicitly states that this system is, quote, not recommended for high-stakes production deployment without significantly larger datasets and more advanced debiasing techniques. It serves as a fantastic educational tool to demonstrate a complete fairness auditing pipeline, but it is a definitive, hard warning against deploying moderate accuracy algorithms into environments where human rights or real security are on the line.
We've seen firsthand today how much effort it takes just to identify and then only slightly mitigate bias in a highly controlled lab setting. So I want to leave you with this. If actively audited algorithms still struggle with fairness, where else might hidden AI bias be quietly impacting your life right now? Thank you so much for joining me for this explainer. Keep questioning the technology around you, and I'll see you next time.